We continue with discrete Markov chains as we look at ergodic theorem. Ergodic theorem. So in this lesson presents a systematic introduction to the ergodic theorem with intuition, formal statements, worked examples, and simulations. First of all, let's start with the intuition about ergodic theorem. So the ergodic theorem answers, do long-term time averages equal averages over all possible states? So we already know in Markov chains, you're moving from one state to another. And now we're asking the question that if you take averages of different state movements over time, is it equal to the average? Does it equal the averages over all possible states? So the two perspectives we have here are about time and space. You have the time average for a Markov chain. So you have a time average 1 over n summation from 0, k equals 0 to n minus 1 of f of t raised to power kx. And then you have the space average integral of f d mu. The theorem states that under certain conditions, the time average is equal to the space average. That is what the whole ergodic theorem thing is about. That under certain conditions, the time average and space average in a Markov chain are equal. So going on from there, we get to see the mathematical setup. So we work with the probability space, which consists of the sample space, the event space, or what you can call the sigma algebra of event, and of course mu, that's the probability measure. Then we have the transformation T, which maps omega to omega, the sample space to the sample to another sample space. Then you have the measure preserving condition such that mu of T inverse of A is the same thing as mu of A. And then you have the function f, which belongs to L1 of mu, like that. And then that takes us to the Beckhoff ergodic theorem, which is one of the most important theorems we see in ergodic theorem. So for a measure preserving transformation T and f, which is an element of L1, we have that the limit as n tends to infinity of 1 over n summation from k equals 0 to n minus 1, f of t raised to power kx equals f star x. This exists, so we are saying that both of them are equal. This exists for almost every x. So if the system is ergodic, then f star x is actually the integral of f d mu, which is the space average, right? So thus, based on the Beckhoff ergodic theorem, time average is equal to space average. So we move on to the definition of ergodicity. So let me see if I can do everything in one blow. Okay, yeah, I think that's possible. So we go for the definition of ergodicity, right? Um, okay, or let me go in bits and pieces. Yeah. So a system is ergodic if T inverse of A is equal to A, implies that mu of A is equal to 0 or 1. And the interpretation is that there's no non-trivial invariant subset, and the system explores entire space. So we have an example for a coin toss system. So let the sample space be h comma t, head and tail. Now one coin has head and tail, and raised power the number of natural numbers you are willing to consider. And then t is the shift operator, and f of x is equal to 1 if first toss is heads, and f of x is equal to 0 if the toss is tail. Then we take the time average here, which is 1 over n integral from k equals 0 to n minus 1 of f t, this t, the shift operator raised to power kx. K is like, so it's more like you now have 1 over n into t0x. That's the first shift. That's the original shift, original position, plus that's f of t0x. Next is f of t1x, f of t2x, all the way to f n minus 1x, like that. Now this counts frequency of heads here. And then the result is that the frequency it tends towards 1 over 2. And of course, that's well established. So if you do the Python thing, right, you have n to be 10,000, this n up here. So it's like you're tossing the coin 10,000 times. So the more you toss the coin, the closer it gets. So in this case now, we have n, then you have the sequence, which is of course random, either 0 or 1. 0 for tail, 1 for head, and you're going for size n, that's 10,000 tosses. And then you take the time average also, which is np dot mean of whatever the sequence is, and then we print the time average and expect and the space average afterwards. And it's usually so as you go higher and higher, as the ptosis gets going, you tend to have the time average and the space average to be about the same. So if you run this, if you keep running, this is random, by the way. So each time you run, you're going to probably get a different result, but the time average and the space average, which is the expected value here, will be about the same. So you see, like it keeps changing, but then the values are pretty close by. Okay, fine. It even gets to that point where you have 0.5, 0.5, like that. Of course, the expected value for the space one for the tosses is there is half, but the time average keeps hovering around that same value. Sometimes it goes a bit less than it and a bit above it. And in few occasions, I mean, so you see the time average and the space average are about the same over time. So we go on to talk about rotation on the cycle, on the circle. So you have a circle, right? You want to talk about rotating on a circle. So define T of x to be x plus alpha mod 1. If alpha is irrational, then so that implies it is ergodic, right? If this alpha is irrational, then we say it is ergodic. So this alpha now is adding the stochasticity to this system, right? Then you have the trajectory now. You have x plus alpha, then you have x plus 2 alpha, and it keeps going on, and it fills the interval 0, 1 uniformly. And then we have the result that 1 over n summation f of t tkx implies integral from 0 to 1 of x dx equals half. Of course, when integral of x dx is equal to half, like that, right? So, and then we can, if you run that, you see the time average is 0.5, like that. Because we already know that the space average is 0.5. So to run the time average, you have n to be 10,000, x is 0.1, and so on and so forth. If you run this, the time average is 0.5, just like the space average, which is already a half, like that. Okay, and then we have this kind of convergence of time average. So you see the time average keeps hovering around 0.5. It goes a bit, it starts like it's above it a bit, and then it keeps going, and then it normalizes around 0.5, like that. So you see 0.5 as we keep running. Okay, it's, you see that 0.5 value there. Then example 3, we have a non-ergodic situation where t of x is equal to x, right? So for t of x equal to x, then we say the time average is 1 over n summation for f t kx, and that is exactly equal to f of x. And this depends on initial value, and it is not ergodic in this case. So then we talk about mean ergodic theorem based on according to von Neumann. So instead of pointwise convergence, we can say that 1 over n summation from k equals 0 to n minus 1 f tkx converges in L2. So then it means we can take the norm. So we have the norm of 1 over n, time average, 1 over n summation f tkx minus the space average expected value of f, second norm, and that approaches 0, meaning that the two values are basically the same because the gap between them is closing up so fast that that norm is going towards 0. So far we have seen the key concept here. We have time average where we have 1 over n summation of f tkx, and then we have the space average, which is integral f d mu. And then ergodicity tells us that time average is equal to space average. So we have some applications of ergodic theorem. First of all, we have it in statistical physics and Markov chains, which we are considering, then in machine learning and dynamical systems. So we have a simple example to work with here. Imagine you have a random walk style experiment. So so of course we are using number here. N is 10,000, and then we make random choice between 0 and 1, tossing a coin, right? Or moving from either 0, having 0 or 1, like that. Then we have the running average, calculated this way, and then the final average ends up being 0.5. And we already know that for a coin toss, right? You are going to, as you toss it several times, the value, the possibility of getting a head or tail or whatever you're focusing on is going to be 0.5. So the time average equals the space average in that sense. In summary, we have that the ergodic theorem states 1 over n summation from k equals 0 to n minus 1 of f tkx approaches the space average, that's integral f d mu. And the key idea is that observing one system long enough gives global statistical behavior. So we have the practice problems. You have the practice problems. Let t of x be equal to x plus alpha mod 1 with irrational alpha. Show that t is measure preserving. We already did exactly this situation. We already have it up here. Where is that now? I think it's came later. So I think that's like moving rotation on a circle. Yeah, exactly this now. And we saw that everything, time average and space average, all go to half like that. So that's that first question like that. Then prove that. Okay, yeah. So here, let f of x be this on this compute f of x dx, all that. So for the system in problem 4 with irrational rotation, determine the time average. So you want to go through all this one after the other. So this is not ergodic. This is the one we just saw now. So let omega be 0, 1, and with fair coin measure, show that the shift map is measure preserving. So it's the idea that time average is equal to space average. So question for a coin toss sequence, compute the expected value of f of x equals x1. So same kind of thing that we've seen. So to compute this, just to integrate this, right, that's x cubed, 1 over 3 x cubed, right? That's 1 over 3 into x cubed. So that's 1 minus 0. So you get 1 over 3 here, something like that. So so for irrational rotation and this, determine the limits of time averages. You can do that, of course, by integrating also. So try your hands on these questions and see how it all goes. With this, I come to the end of Ergodic theorem, which tells us that as a process goes on, as a stochastic process goes on over time, the time average becomes equal to the space average, roughly, right? So yeah, let me know how this helps you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, what exactly are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. So subscribe and hit the notification bell so you can get alerted. You can also become a member of this channel by clicking on join. That gives you some special privileges you find out when you click on join. Like you get to see some videos first before other people, or you get to see some videos exclusively, and because you're a member, you can also request for PDF copies of my notes. We can have a sit out, so to speak, like we can hang out together to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.